A team of British scientists just did something researchers almost never do. They wrote an obituary in advance for a piece of ice roughly the size of a small country, because they are now confident enough in what they're watching to say in plain language that it is going to die. The ice in question sits at the front of Antarctica's Thwaites Glacier, the single most closely watched, most feared glacier on the entire planet, nicknamed the Doomsday Glacier for a reason that has nothing to do with media hype and everything to do with what happens to the world's coastlines if it goes. And according to the scientist who runs the British side of the international research collaboration studying it, the last natural break holding that glacier back is now, in his words, poised to disintegrate. Today, we are breaking down exactly what scientists have found, in their own words, why this specific warning is different from the doom-laden headlines this glacier has generated for years, and what it actually means for coastal cities around the world if they're right. No exaggeration, just the science and the stakes. If rising sea levels have affected where you live, tell me in the comments. And subscribe now if you want to keep tracking this story as new research comes in. Let's get into it. To understand why this warning matters, you first need to understand exactly what Thwaites Glacier is, and why scientists picked this specific glacier out of the thousands scattered across Antarctica to worry about the most. Thwaites sits in West Antarctica and is roughly the size of Florida, or depending on which comparison you prefer, roughly the size of Great Britain. It is one of the widest glaciers on Earth, and it has been losing ice at an accelerating pace since the 1980s, shedding hundreds of billions of tons of ice and retreating approximately 12 miles since 1992 alone. If Thwaites Glacier were to collapse entirely, scientists estimate global sea levels would rise by roughly 65 centimeters, just over 2 feet on their own. That number sounds almost manageable in isolation. It is not, once you understand what a 2-foot global sea level rise actually does to coastal infrastructure. And it gets far worse once you understand what Thwaites is connected to. It's worth pausing to explain exactly what an ice shelf is and how it differs from the glacier itself, because that distinction is doing a lot of work in this story, and it's easy to blur the two together. A glacier like Thwaites is grounded ice, meaning it sits directly on bedrock, in this case, bedrock that lies well below sea level across most of the glacier's footprint. As that grounded ice flows toward the coast, it eventually reaches the point where it starts floating on the ocean rather than resting on solid ground beneath it, and that floating extension is the ice shelf. Because it's already floating, an ice shelf breaking apart does not, by itself, add meaningfully to sea level. In the same way, an ice cube melting in a glass of water that's already floating doesn't raise the water level. The real danger isn't the shelf's own mass, it's the shelf's function as a physical barrier, wedged against an underwater ridge, that restrains how quickly the grounded ice behind it can flow into the ocean. Remove that barrier, and the grounded ice, the part that genuinely does add to sea level once it melts, starts moving faster toward the water. That's the entire mechanism driving concern here, not the disappearance of the shelf itself, but what its disappearance unleashes behind it. Here's the detail that turns Thwaites from merely concerning into the reason scientists reach for words like doomsday without irony. Thwaites does not sit in isolation. It occupies a deep basin that sits below sea level, and it sits directly in front of a much larger, much more dangerous structure, the West Antarctic ice sheet. Because of how this specific region of Antarctica is shaped, with the bedrock dipping downward as you move inland rather than rising the way it does under most glaciers, once ocean water finds a way underneath the ice, it does not simply erode the front edge. It can melt its way inland, undermining the ice from below and effectively freeing entire sections of the ice sheet from the bedrock they're currently anchored to. Robert DeCanto, a glaciologist at the University of Massachusetts Amherst who studies this exact dynamic, has described the stakes in stark terms, saying that a collapse of the entire glacier, something researchers believe could take place over a matter of centuries rather than decades, would represent a genuinely global change, one significant enough that our coastlines would look visibly different even viewed from space. And because Thwaites sits at the gateway to the broader West Antarctic ice sheet, which alone holds enough ice to raise global sea levels by roughly 3.3 meters, or about 10.5 feet, its loss threatens to destabilize a system that dwarfs the glacier itself. Now, to the specific warning driving headlines right now, the one that separates 2026 from the years of steady, gradual concern that came before it. Thwaites Glacier is not just a wall of ice sitting on land. At its seaward edge, it has an eastern ice shelf, a floating extension of the glacier that juts out into the ocean, held partially in place by an underwater ridge, acting like a natural doorstop. That ice shelf's entire job, functionally, is to act as a brake, physically restraining how quickly the ice behind it can flow out into the sea and eventually melt. For years, that eastern ice shelf has been the thing standing between Thwaites' current slow decline and a much faster one. According to Robert Larder, the marine geophysicist who coordinates the UK side of the international Thwaites Glacier collaboration, that brake is now failing in real time. Speaking directly about the eastern ice shelf, Larder said plainly that the last bit of ice shelf in front of the glacier is poised to disintegrate, and that while scientists don't know exactly how the breakup will unfold, they are certain, in his words, that it is definitely going to go. He has described watching the ice shelf tear away from the glacier, its internal structure growing visibly more fragile, with fractures and rifts expanding across successive satellite images. Larder is not speaking loosely here. He and his colleagues at the British Antarctic Survey have gone as far as writing what they themselves describe as the ice shelf's obituary, a striking, deliberate choice of language from scientists who spend their careers being cautious about overstatement. Larder has said the breakup is very likely to happen sometime within 2026 itself, meaning this is not a distant, hedge-everything, decades-out projection. It is a specific, near-term forecast from the researchers who have spent the last 8 years, since the International Thwaites Glacier collaboration first formed in 2018, studying this exact stretch of ice more closely than almost anywhere else on the planet. The physical evidence backing up that warning has been mounting steadily throughout 2026, and it comes from multiple independent research teams using entirely different methods, which is exactly the kind of convergence that makes scientists confident rather than speculative. A study published in the Journal of Geophysical Research, using 2 decades of satellite imagery, found that fractures within the ice shelf's critical shear zone have been expanding in a specific, recognizable pattern. Long shear fractures growing first, followed by a spike in smaller fractures branching off from them. That pattern matters because it lets researchers distinguish between ordinary background ice fracturing, which every ice shelf experiences to some degree, and the specific structural signature that precedes a genuine large-scale breakup event. Researchers from the University of Manitoba, led by glaciologist Karen Alley, analyzed satellite data spanning 2002 to 2022 and found that the total combined length of fractures across the shelf grew from roughly 100 miles to more than 200 miles over that period. Alley has described the transformation in direct terms, saying the ice shelf has gone from being a thick, strong structure to a thin, weak one that is now breaking apart at the exact point that used to hold it in place. Christian Wild, a geophysicist at the University of Innsbruck in Austria who has also studied the shelf's recent behavior, described what current satellite imagery shows using a comparison that has stuck with almost everyone who has covered this story since, saying that large areas of the shelf are suddenly falling to pieces and that the process looks like a windshield shattering. The speed of the underlying physical changes is what has pushed this from a long-term concern into an active, near-term warning. According to Wild's research, the eastern ice shelf's flow speed, essentially how fast the ice itself is moving toward the ocean, more than tripled between January 2020 and January 2026, climbing to just over 2,000 meters per year, with further acceleration recorded in the months since. In a related study, Wild and his colleagues found that the grounded glacier ice directly behind the shelf, the ice that the shelf's buttressing effect is specifically supposed to hold back, sped up by roughly 33% over that same period. Ted Scambos, a glaciologist at the University of Colorado Boulder who has also studied Thwaites extensively, has pointed out that losing the eastern shelf entirely will directly affect how quickly the broader glacier changes and how large a share of future sea level rise it ends up contributing. Put those two figures side by side and the picture becomes clear. The shelf itself is moving nearly 3 times faster than it was just 6 years ago, and the ice it was built to restrain is already responding by speeding up and step behind it, even before the shelf has finished breaking apart entirely. Beneath all of this visible fracturing and acceleration lies the actual physical mechanism driving the entire process, and it is worth understanding clearly because it explains why this kind of ice loss is so difficult to reverse once it starts. Thwaites is not primarily melting because warmer air is sitting on top of it, the way a typical mountain glacier retreats. It is being attacked from below and from the ocean side by warm, salty water pushing up from several hundred meters deep in the Southern Ocean. According to Larder, there was a specific shift sometime in the middle of the 20th century in how this deep, warm water gets circulated and delivered toward the Antarctic coastline, a shift driven primarily by changes in the wind patterns that control Southern Ocean circulation. Those wind pattern changes are themselves part of the broader pattern of human-driven climate change, and once that warm water reaches the base of a glacier like Thwaites, sitting on bedrock well below sea level, it begins melting the ice from underneath, at exactly the point where the ice meets rock, a configuration that makes the resulting melt extremely difficult to slow down once it has properly begun. Recent field research has added a genuinely unsettling new layer of detail to that basic mechanism. Using ice-breaking research vessels and an underwater robot called IceFin, scientists working with the International Thwaites Glacier collaboration discovered that seawater is actively moving more than 6 miles beneath the glacier itself, intruding far further inland under the ice than researchers had previously understood. That subglacial seawater intrusion intensifies melting in exactly the hardest to observe, hardest to model part of the entire system, the zone where grounded ice meets bedrock, far from the visible, photographable edge of the glacier. Separately, a study published in the journal Science Advances in May 2026 documented what researchers describe as a fundamental shift in the ocean surrounding Antarctica as a whole, with heat that had previously remained trapped at depth now rising toward the surface, where it becomes capable of accelerating sea ice loss on top of the direct glacial melting already underway. It also helps to understand exactly how researchers have been able to study a location as remote and hostile as Thwaites closely enough to make claims this specific, because the fieldwork itself is genuinely extraordinary. The International Thwaites Glacier Collaboration, the joint US-UK research effort Larder helps coordinate, has sent teams onto the glacier itself using ice-breaking research vessels to reach the surrounding ocean and specialized drilling equipment to bore directly through hundreds of meters of ice to reach the water and bedrock below. Well, one of the collaboration's signature tools is IceFin, a torpedo-shaped underwater robot purpose-built to swim beneath the ice shelf and directly measure water temperature, salinity, and current speed in places no ship or diver could safely reach. Earlier expeditions have found that the water directly beneath Thwaites' main trunk is both warmer and faster flowing than researchers had previously modeled, and that swirling eddies of water measuring up to 6 miles across are actively circulating beneath the ice shelf, drawing warmer water inward and carving out valleys in the underside of the ice that Cornell oceanographer Peter Washam has described as genuine hotspots of melting. This is not satellite imagery interpreted from a comfortable research office. It is scientists physically drilling into one of the most remote, dangerous stretches of ice on the planet, at the edge of a continent that regularly produces some of the coldest temperatures recorded anywhere on Earth, specifically to get direct measurements that satellite data alone cannot provide. Given all of that, it is worth asking directly, does Robert Larder, the scientist who has spent 8 years studying this glacier and coordinates the entire UK research effort, actually think the Doomsday Glacier nickname is fair? His answer, in a direct interview, is worth hearing in his own words rather than paraphrased into something more dramatic than he intended. Larder has said that when the nickname first emerged, the research team resisted it because it felt like it prejudged conclusions they hadn't yet reached. But after 8 years of accumulating results, he has said he increasingly thinks the name is appropriate, adding plainly that the team's results point toward Thwaites eventually being lost entirely. He was careful to add an important caveat immediately afterward, that the specific time frame for that loss remains the biggest open scientific question, and that while most researchers working on Thwaites are convinced its retreat will not stop, predicting exactly how many decades or centuries that retreat will take is still an active area of ongoing research, not a settled number anyone can state with high confidence. That distinction matters enormously for how anyone should actually interpret this warning, and it is where a lot of casual coverage of Thwaites tends to go wrong. Losing the eastern ice shelf this year does not mean the entire glacier collapses this year, or even within the next several years. Larder has been explicit that an ice shelf is not the same thing as the glacier itself, that the glacier is a couple of orders of magnitude larger in area than the shelf sitting in front of it, and that what's actually happening in 2026 is the loss of one specific stabilizing structure, not the disappearance of the glacier as a whole. What losing that structure does mean is that the break holding back the glacier's flow into the ocean gets meaningfully weaker, which is expected to accelerate Thwaites' overall rate of ice loss over the years and decades that follow, even though the full 65-centimeter sea level contribution from a complete Thwaites collapse remains, by every current estimate, a matter of centuries rather than years. Here is where the human stakes actually come into focus, and why researchers like Larder keep pushing to communicate this clearly, despite how easy it is for the public to tune out numbers measured in millimeters. Current global mean sea level rise sits at roughly 4 to 4.5 millimeters per year. On its own, that number is genuinely difficult to get anyone alarmed about. And Larder has acknowledged that directly, saying it's hard to generate real concern over an extra millimeter here or there. But the actual danger isn't really about the raw millimeter count. It's about how a comparatively small overall rise in sea level disproportionately increases the frequency of coastal flooding events. Larder's own explanation is the clearest version of this argument available. You do not need a large amount of sea level rise, just a meter or two, to turn what used to be a once-in-a-century coastal flooding event into something that happens once a decade, or even annually, in vulnerable coastal cities. Major population centers including New York, Boston, San Francisco, and Miami are already grappling with early versions of exactly this dynamic. An accelerated ice loss from Thwaites and its neighboring glaciers is one of the primary long-term drivers pushing that risk higher for coastal communities worldwide, forcing difficult, expensive infrastructure decisions about coastal defenses that many cities are only beginning to seriously plan for. There's one final piece of this story that deserves attention, because it is arguably the most consequential part of the entire warning, and it extends well beyond Thwaites itself. Larter has pointed out that Thwaites does not exist in isolation within West Antarctica's broader ice system. The instability driving its retreat, the fact that the glacier sits on bedrock lying well below sea level, is shared by several of its neighboring glaciers across the same region, including the nearby Pine Island Glacier, which has shown similar patterns of accelerating retreat over the past 2 decades. That means the loss of Thwaites specifically is likely to help destabilize those neighboring systems as well, rather than representing a contained, isolated event. Taken together, Larter has said the West Antarctic ice sheet as a whole represents a total sea level rise commitment of more than 3 meters, nearly 10 feet, a scale of change that, in his own words, will not be something this generation has to directly confront, but one that is being locked in by decisions and emissions trajectories playing out right now. So where does that leave the actual forecast for 2026 and beyond? The eastern ice shelf's breakup, according to the scientists most directly studying it, is very likely to happen within this year. And when it does, satellite imagery is expected to capture a visually dramatic sequence of the shelf fragmenting and drifting away. The kind of imagery that tends to generate exactly the viral, alarmed headlines this glacier has produced for years. What matters more than that imagery, according to the researchers themselves, is what happens to the glacier's flow rate in the months and years that follow, as scientists watch to see exactly how much faster ice moves toward the sea once its main natural break is gone. That is the genuinely open question driving ongoing research right now, and it is the reason the international collaboration studying Thwaites has no plans to stop monitoring it once this specific ice shelf finally breaks apart. It is also worth noting that this entire warning sits within a much larger pattern of accelerating change across the Antarctic continent as a whole. Separate research published earlier this year has documented that Antarctica's overall sea ice extent has reached some of the lowest levels ever recorded in the modern satellite era, with an area of missing winter sea ice roughly the size of Texas that scientists now believe is unlikely to fully return, part of the same broader shift in ocean heat distribution around the continent that is compounding the direct melting pressure on glaciers like Thwaites. We will keep tracking every new study and every satellite update on Thwaites as this story develops. This is very likely not the last major update this glacier produces this year either, given that the eastern ice shelf's breakup itself is still actively unfolding as of this recording, and researchers monitoring the site have said they are watching the site daily for signs of the final structural failure. If this gave you a clearer picture of what's actually happening in Antarctica right now, subscribe so you don't miss the next update, and drop a comment letting me know what you think this means for the future of your own coastline. Stay curious, stay informed, and I'll see you in the next one.